Welcome back to our lessons on series and parallel circuits. This lesson, number 2, is going to compare the potential difference in the circuits. Right, just a reminder, a series circuit has only one path for the current to flow. So if we look at our series circuit with an ammeter to measure the total current and resistor R1 connected in series to resistor R2, which is connected to a closed switch, we say that the potential energy of the cell is 1.5 volts, and we would say that R1 has the same resistance as R2, meaning that they are identical. If we connect a voltmeter across the battery to read the total available volts to the circuit, it would measure 1.5 volts. Now, 1.5 volts represents 1.5 joule per coulomb charge. So we must remember that this is the energy available per coulomb charge to the circuit. Now, our connectors, as well as the ammeter, has no resistance. So technically speaking, they would not use any energy to move the charges through them. It's once we get to the resistors, when the charge wants to move through the resistors, it requires energy to move the charge through the resistor. Now, if the resistors are identical, then they would split the energy in half. So the total amount of energy supplied is 1.5 volts. So the first resistor would use half of that energy, which is 0.75 volts. The reading on V1 would be 0.75 volts. And the other half of the energy would be used to push the charge through resistor 2, so 0.75 volts would be used to push the charge through resistor 2. So we can conclude that the total voltage in a series circuit would be the sum of the potential drops across the resistors. In my example, just to make the understanding simple, I used identical resistors, so the potential difference would split in half. It won't be the case if the resistors are not identical. To move on to a parallel circuit where an ammeter is used to connect to measure the total resistance, and resistor R1 is connected in parallel to resistor R2. Now the strangest thing happens here. Because the total current divides and can flow now simultaneously through the two resistors, the 1.5 joules per coulomb energy that is supplied to the circuit, we call that the total voltage, is used to push the charge through resistor R1 as well as R2 in the same time. So the voltage drop across R1 would be the same as the voltage supplied by the battery, and the voltage drop across R2, V2, would be the same as the voltage drop across the battery. So here we see, and we will see if we do it in a practical way, that the total potential energy per Coulomb charge supplied by the battery is equal to the energy used per Coulomb charge by resistor R1 and equal to the energy used by resistor R2. What we can do is we could connect one voltmeter across the parallel combination, and I want to show you how we can draw that situation. We can have a voltmeter across the parallel combination here. I'm going to call it VP. That would read 1.5 volts. The two resistors act as one, basically, both of them connected to the 1.5 volt at the same time. So they take the same work per Coulomb charge to push the current through them. I hope this is a simple enough explanation to what we find in series compared to parallel circuits. So a series circuit is called a potential divider. And from the previous video, we know that the parallel circuit is a current divider. Right, we'll meet again in the next video, where we will discuss the resistance in the circuit. Thank you for watching.